Welcome back to Differential Equations. In this video, we want to talk about linear autonomous systems. Remember that an autonomous system is a system of differential equations that can be written in the form x prime equals some f of x and y prime equals some g of x and y. And we're going to study the two-dimensional dynamical systems here because it gives us phase planes that we can draw, but the same definition extends to 3 or 4 or 27 dimensions. The important thing is that these functions on the right-hand side have x's and y's, but not t's. Functions do not change over time. If we want to study a linear autonomous system, then very specifically, our function must be a linear function. So we'll have some a times x plus some b times y. And yes, technically we could have some constant. If you've studied linear algebra, adding a constant c here makes this affine, not linear, but that's close enough. And outside of the study of linear algebra, the vocabulary gets really messy. And okay, now we're using e, which looks like the exponential, and we're using f that looks like the name of one of our functions, but we'll just shrug and ignore that because for the systems we're going to be studying, we're actually going to simplify things even further. Because it turns out that just simplifying things into these linear systems actually gives us enough detail to get to every interesting thing that can happen in a phase portrait. All right, let me get my head out of the way, and rather than trying to explain that, let's just dive in. All right, we're going to start with the simplest phase portrait that I can come up with. X prime equals x, y prime equals y. This one and all of the phase portraits that we're going to study in this video are simple enough that we can plot them without having to resort to using a computer because they're going to be that simple. Right, so we have our coordinate axes. There is exactly one equilibrium point in this and pretty much every dynamical system we're going to study in this video. That will be at 0, 0. And let's see, if x is positive, then x is going to grow. If x is negative, then x is going to shrink or grow in the negative direction. Likewise, if y is positive, y will grow, and if y is negative, y will shrink. So let's make that a little bit beefier so that we can actually see what's happening. All right, so we're going to grow in the x direction. We're going to grow in the y direction. We're going to grow negatively in the x direction over here. We're going to grow negatively in the y direction over there. And if we're somewhere in the middle, we're going to be somewhere in the middle. We have an equilibrium point, a node at the origin. And no matter where we try to go, the graph is going to try to push us away from that equilibrium point. And it's going to push us relatively in a straight line. This is referred to as simply an unstable node, or sometimes you'll see it referred to as a nodal source. Flipping this around just a little bit, if I've got my x prime is the opposite of x and y prime is the opposite of y, well, once again, we have our equilibrium point at 0, 0. But if we're over here on the positive x-axis, x is positive, so x prime is negative, and we're going to go this way. If we're on the positive y-axis, we're going to go down. If we're on the negative x-axis, we're going to move in the positive x direction. And if we're on the negative y-axis, we're going to move in the positive y direction. And then if you check anything in between, it will continue following the same pattern. And so no matter where you are, the dynamical system is going to try to push you towards the origin, towards 0, 0. So in this particular case, this is a stable node. And vocabulary, sometimes you'll also see this referred to as a nodal sink. Right? What if we mix it up? What if we have x prime equals x and y prime equals negative y? We have one positive, the other negative. Well, as I've drawn this, we're going to be looking at x going this way or that way. We're going to have our equilibrium point at the center. And then y is going to go in the opposite direction. Positive y is going to go down, negative y is going to go up. And then what will it be in the middle? Well, I guess over here it's going to kind of go in that direction, and in that direction, and like that, and like that. Right, to sketch this out a little bit more neatly, I'll introduce you to one of the properties of a phase portrait, which is that a phase line can never cross a different phase line. That's something that you've seen in your study of fields in other aspects in calculus. So this curve kind of has to be asymptotic, right? In the first quadrant, it has to be coming down from the y-axis, but it can't cross the y-axis. It has to be going out along the x-axis, but it can't cross the x-axis. So you end up with these asymptotic curves coming near but not touching the axes. And if we extend out, they'll just continue onward like that. This is referred to sometimes as a semi-stable node, although technically it's mostly an unstable node, right? As we've drawn this one, if you are on the y-axis, you stay on the y-axis, so it becomes stable in that sense. But if you are anywhere else, you go away. This can also be referred to as a saddle point or a saddle node. This picture is a little bit hard to follow, so I think it's worth going over to the computer software and just plotting a couple of representative curves. Make sure that this whole thing is making sense. Fill in the gaps a little bit more. Yeah, something like that. So we're going to be following these paths that kind of try to come towards that equilibrium point, but then end up flying away. And it's very difficult to hit exactly on, but I did want to point out that if you are really close, it's hard to tell that there is any curve whatsoever because it almost looks like it's forming a right angle at that equilibrium point. But as you're further away, I think that's the picture that's more worth remembering. All right, let's get back to my notes. You don't need to see me, you want to see what I'm writing. And let's continue onward. So we've looked at the cases where we have x and y kind of just doing their own thing. What if we swapped them? X prime equals y, y prime equals x. This is one of the first places where things can get a little bit interesting because it's going to take some thought. Although we will see that this one is not all that different from what we've just seen. Right, so we do still have an equilibrium point at the origin. Then x prime is equal to y. So if we are up here, we're going to be growing in that direction, and if we are down here, we're going to be growing in that direction. y prime is equal to x. So if we're over here, we're going to be growing up, and if we're over here, we're going to be growing down. In the middle, I guess everything is going to fall away. So if x and y are both positive, we'll be going this way. If x and y are both negative, we're going to be going that way. If x is negative but y is positive in the second quadrant, well, if x is negative, we're going to be going down. If y is positive, we're going to be going to the right, and we get something that looks like this. In the fourth quadrant, we have that x is positive, so we're going to be going upward, but y is negative, so we're going to be going to the left, and we end up with a shape that looks like this. And this is not obvious at first glance, but if you think about the fact that you're not allowed for the equilibrium lines, or I'm sorry, the phase lines to cross each other, then that means we're going to have these curves that look like this. And if we go back to our computer graph, I think it becomes a lot more clear that the thing we're looking at is the same saddle node that we saw before, just rotated by 45 degrees. All right, so this thing is also a saddle node. See if I can get some lines real near the origin to kind of make it a little bit more clear what's happening there. There we go. Just take the picture that we saw from the previous example and rotate it by 45 degrees, and you end up with this picture. Canonically, classification-wise, it is the same graph. We're still going to call it a saddle node. You don't need anything different. But if we change one or the other of these, then things get interesting. If we change them both, we're just going to have kind of the opposite saddle node. Right? If x prime is negative y and y prime is negative x, then all of the arrows change direction, but it's the same basic picture. It does get interesting. It helps if I can write the thing that I'm trying to write. If we only change one of them, so x prime equals y, y prime equals negative x. We changed one but not the other. Now we're going to end up with a more interesting curve. Because up here, where y is positive, x is increasing. When x is positive, y is decreasing. When y is negative, x is decreasing. And when x is negative, y is increasing. So we end up with this thing that's going to form loops. Right? If we try to look at the things in the middle, it's going to be just halfway in the middle. This is a construction that is called a center. And I guess once again, coming back to the computer software will help us out. In the linear case that we are studying here, a center forms concentric rings. This should look familiar to you. These are all limit cycles, and they are just the nicest form of limit cycles. All right. So there are some other things that can happen, and those other things tend to happen when we kind of mix what is happening with different variables. So instead of just leaving things alone, what if we set x prime equals x minus y and y prime equals x? Now we have a couple of variables going on. I guess we can try to graph this out, but it's a little bit harder to understand. So we are definitely going to be going to the computer software before we end it. It turns out that these two lines are going to be very useful to us, x equals y and x equals the opposite of y. Because we can start off with y prime. Y prime equals x, so we're going to be going upward here, and we're going to be going downward over here. But x prime is x minus y. So when x and y are equal, x is not going to be changing. Y still might be changing, but x will not be. So if x and y are equal like they are here, we're also going to be going straight up and straight down. If y is 0, as we see on the x-axis, well, we said that we were going to be going upward in the y direction, but we'll also be going in a negative x direction. And then over here, I'm sorry, I set that up backwards. Right. When x is positive and y is 0, we're going to be going upward in the y direction, but also outward. So I guess this is going to be more like that. And then when x is negative, we're going to be going outward kind of more like that. So this is a little bit harder to follow. Again, luckily we have some computer software to help us. So let's sketch out a couple of representative curves. And if you notice, the arrows are all kind of pointing outward. So this is a source. It is an unstable node. But it doesn't just go in straight lines. It goes in curves. So this construction is known as a spiral source. And generally we're looking at a graph that's going to do things like that. And yes, there will be multiples of them, but everything originating from that center point. I usually try to draw 3. Sometimes I'm better at it than others. Let's try this whole thing again. See if I can get it a little bit cleaner. But yeah, I generally find that drawing 3 of the curves makes it the nicest midway between readable and interesting. But yeah, something like that, kind of, sort of, mostly. And then if we change things around, we can get this to go inward instead of outward. All right, so notice that I've just taken the negative on x prime and y prime so that all of my arrows are going to change directions, and it's going to be the same kinds of curves, but instead of going outward, they are all going to go inward and do things kind of like that. So everything is going towards the center instead of away from it. So that's the 6 canonical forms of phase planes that all can come up from linear systems. And yes, we can come up with a couple of other examples, a couple of other ways of writing, especially the spiral source and spiral sink. But we have nodal source, we have nodal sink, we have saddle node, we have a center, we have a spiral source, and a spiral sink. And most of the time, we're going to end up with one of those. Although before we wrap up, I do want to mention that there is one other thing that can happen, and that's where the system of equations gets interesting algebraically. So here is one such example where x prime is equal to x, y prime is equal to 0. And that second equation gives us no information. We want to know when is x prime equal to 0 and when is y prime equal to 0 to find the equilibrium point. And we had been looking at the situation where there was exactly one equilibrium point. It turns out that there will never be a situation where there is no equilibrium point. To have that sort of a situation, we'd be dealing with things that make it not quite an autonomous equation anymore, and so we don't have to worry about that. But we can have situations where there are infinitely many equilibrium points. So if I jump over to the phase plane software once more, you can see that whenever you click here, the entire y-axis is an unstable node, and everything is just moving directly horizontally away from that unstable node in either direction. I can't actually click exactly on the y-axis, but if you clicked exactly on the y-axis where x is equal to 0, you would have an equilibrium point, and it would just stay there like that. Great. So this is a construction that is known as an irregular node or an irregular equilibrium points. Again, my equilibrium points in this case are 0, y for every y. And I want you to look at something similar. One of the ways that a system can break down algebraically is when one of the equations just isn't there. The other way that a system of equations breaks down algebraically is when it's not actually a system, but the same equation multiple times. So why don't you take a look at this system. X prime equals x minus y prime equals x minus y, and see what you can come up with to describe it. Certainly, take a look at what the phase plane will look like and make sure that you can make sense of that. See if you can describe where the equilibrium points are or anything else that you might be able to find interesting about it. See what you can do with that, and I'll see you in the next video.